All right, so in this video, we're going to be looking at Lewis structures. Now, Lewis structures in both this class and in next grade 12, next year's class, it's going to be probably one of our most important tools. So Lewis structures, I always like to think of like a puzzle, and it's going to be our way to actually draw compounds. So now that we understand a little bit about compounds, types of compounds, we're going to look at drawing some of those compounds. So we're going to look at drawing Lewis structures for two different compounds, ionic compounds and molecular compounds. Just a reminder, you did start reviewing these in grade 9. So ionic compounds, we know in grade 9 we said was between a metal and a nonmetal. Now we say ionic compounds are between two things that have an electronegativity difference of greater than 1.7. Molecular compound, in grade 9, we said it was between two nonmetals. Now we say it's something that's got an electronegativity difference of less than 1.7. So we understand a little bit more about these compounds. Now let's look at drawing these. Before we look at drawing them, I want to talk about some terminology that's going to come up and what it's going to look like. So we're going to be looking at electrons and pairs of electrons. So the term lone pair, when I say lone pair, that means electron pairs that are not being used in bonding. So it means that electrons that are going to be present but aren't necessarily going to be in a chemical bond. A lone pair, you've actually seen these before. It's just those two electrons that might be hanging out at the top of an atom. So for example, if I was going to draw the Lewis diagram of oxygen, remember that oxygen has 6 valence electrons. For Lewis diagrams, I'm only drawing valence electrons. So for my 6 valence electrons, 2, 3, 4, 5, 6. So you can actually see two sets of lone pairs here on oxygen. I can see a lone pair here, right? 2 electrons by themselves. And I can actually see a lone pair down here, 2 electrons by themselves. So a lone pair is just going to be 2 electrons that aren't necessarily involved in bonding at all. On the other hand, we have something called a bonded pair, and a bonded pair represents a share of paired electrons. So when we have 2 electrons that are going to be shared together, my dog says hi, when we have 2 electrons that are going to be shared, hi buddy, we have 2 electrons that are going to be shared together, we are going to represent it 2 different ways. So the first way we're going to represent it is if we have 2 electrons from 2 different atoms that are being shared, we're going to go ahead and we are going to circle them. That's going to represent that they're being shared. Now that really doesn't look great, right? It's going to make our diagram kind of messy. So we're actually going to simplify a shared bond by just a straight line. So some of you actually might remember this from grade 9 or grade 10. You might have seen myself or one of your other science teachers sketch something on the board with a line between 2 different atoms. That just means that a bond has been formed, a bonded pair. We can have a couple different types of bonds. So we can have, gotta get rid of this first, and then I'll scroll. There we go. Better. Okay. So we can have a couple different bonds. We can have something called a single bond, a double bond, or a triple bond. A single bond means that I just share one pair of electrons. So if I'm only sharing one pair of electrons, I'm only going to draw one straight line. If I'm sharing 2 pairs of electrons, that's a double bond. I'm going to draw 2 straight lines. And if I'm sharing 3 pairs of electrons, that's a triple bond. And I'm going to draw 1, 2, 3 straight lines. So it's important to understand the difference between single, double, or triple bonds as we go into these diagrams. All right, so let's start by drawing the Lewis structures of ionic compounds first. Many students actually find these easier. So just a reminder that ionic compounds are going to have a metallic and a non-metallic element. So it's really important to understand metals and non-metals in the periodic table. And even better, in grade 11 chemistry, we look at electronegativity differences. So an ionic compound is going to have an electronegativity of greater than 1.7. So when you're drawing Lewis structures of compounds, it's important to first know what type of compound you have. So you first want to make sure that you do indeed have an ionic compound. If you do have an ionic compound, these are the steps that you're going to take. You are going to determine the charge of each ion and place it outside of the square bracket. And you are going to be sure that all ions are next to opposite charges. So sometimes these instructions can kind of be confusing. Sometimes it's just easier to do it. So we're going to go ahead and we're going to try our first example here. And we're going to follow these 2 steps. So we're going to take a look at lithium chloride. So first thing that you want to do is you want to make sure that you're dealing with an ionic compound. So lithium is a metal, chlorine is a nonmetal. So yes, this is an example of an ionic compound. If you don't trust me, go ahead, pause the video and check out the electronegativity differences, and you're going to find out the electronegativity difference between lithium and chlorine is higher than 1.7. So what I want to do, I call it rough work to start. So I just want to see what I'm working with. So I'm going to draw the Lewis structure of lithium, and I'm going to draw the Lewis structure of chlorine. Now, if you skipped over that lesson that's called drawing atoms, that was the review from grade 9, I would go back and I would watch it, because you need to know how to draw the Lewis structure of atoms before you can draw the Lewis structure of compounds. So my Lewis structure of an atom is just going to be my valence electrons. So I want to see how many valence electrons there are in lithium. To see this, I would go ahead, I would find lithium on the periodic table. Lithium on the periodic table is in the first group. Anything in the first group has 1 valence electron. Then I would find chlorine on the periodic table. Chlorine is a halogen, group 17. So anything that's in group 17 has 7 valence electrons. So by doing this rough work, all that I'm doing is I can just go ahead and I can see what valence electrons I have to work with in this case. Now that I actually have my Lewis diagrams or my rough work, what I want to do is, remember, in an ionic bond, I'm dealing with ions. So I want to see what the ion of lithium looks like, and I want to see what the ion of chlorine looks like. So the ion of lithium is going to look like this. I want to have a full valence shell. So in this case, I have to think, is it easier to lose 1 or to gain 7? Well, I'm going to lose 1. If I lose 1 negative, my overall charge is going to be positive 1. To show it's an ion, I want to go ahead and I want to place it within square brackets. So if you're kind of stuck on this, I would go ahead and I would pause this and I would rewatch the forming ions lesson. So make sure you didn't skip the forming ions lesson. You're going to need that for these ionic compounds. So just a reminder, step 1 says determine the charge of the ion and place it outside of the square bracket. So we did that. We determined the charge of lithium and we placed it outside of the square bracket. Now I want to do the next for chlorine. So chlorine, we have to think about what it's going to form as an ion. Is it easier? Chlorine's got 7 valence electrons. So is it easier to gain 1 or is it easier to lose 7? Well, in this case, it's going to be easier to gain 1. So my overall charge for chlorine is going to be a negative 1. Now, technically, to make this diagram correct, you would want to show the full valence shell of chlorine. So to be totally correct, you'd want to have the full valence shell of chlorine. I want you to know I'm never going to take marks off for this. Most chemists actually take the shortcut of just the square brackets and the charge. So oftentimes when you're reading chemistry textbooks, you might not see that full valence shell of your negative ion, but to be totally correct, you do want to show it. So in this case, we want to make sure, finally, that all ions are next to opposite charges. What I mean by this is it's the electrostatic attraction between a positive and negative that forms a bond. It's like magnets. So you want to make sure you have a positive and a negative actually next to each other. Well, in this case, I have my positive. In this case, I have my negative. They're next to each other. And a really good way to check as well, too, all ionic compounds are going to have what's called charge balance. So all ionic compounds are going to have, if you've drawn them correctly, the charges add up to 0. So it's a really good check to make sure that you're correct. If I have positive 1 and negative 1 and I add them together, that's going to go ahead and it's going to add to 0. So now would be a great time to go ahead, pause the video, and I want you to go ahead and try aluminum bromide on your own. Come on back and I'll show you how to actually take up that answer. All right, so let's go ahead and let's go through aluminum bromide. So again, I want to start with my rough work. So I want to see what aluminum is going to look like, and I want to see what bromine is going to look like. Now again, a good habit is to check and to make sure that you actually have an ionic compound. Aluminum's a metal, bromine's a non-metal, so I am dealing with an ionic compound. Aluminum is in the third column, or 13th group, sorry, of the periodic table. 13th group has a valence electron of 3. So we have 3 valence electrons for aluminum. 1, 2, 3. Bromine is a halogen. It's on the 17th column. So bromine is going to look like this with 1, 2, 3, 4, 5, 6, and 7. Now again, I want to go ahead and I want to determine the ions of both. Now this one's actually a little bit different because if you take a look, we have a different number of ions present. So aluminum, there's no number written next to aluminum, so we go ahead and we assume that's a 1. But this 3 next to bromine means that you actually have 3 bromine ions. So when we draw bromine, we're actually going to have to draw it 3 times. So let's go ahead and let's take a look at what this is going to look like. Let's start with aluminum. So aluminum has 3 valence electrons. We have to ask ourselves, is it easier to lose 3 or gain 5? It's easier to lose 3, so I'm going to have an overall charge of positive 3. I put my square brackets around to tell me that it's an ion. For bromine, again, I have to ask myself, is it easier to gain 1 or to lose 7? Well, of course, it's going to be easier to gain 1. So my charge for bromine, if I'm gaining 1 negative, my charge for bromine is going to be -1. And again, my square brackets. Now, to be totally correct, you want to show that full valence shell here. A lot of chemists skip this step. All right, so my last step is I need to draw 2 more bromines in order to be totally correct. Now remember, my rule number 2, or my step number 2 says I want to make sure that all positives and negatives are touching. So if I go ahead and I draw another bromine over here, well, that's a negative and a negative together. There's nothing actually holding together that bond. Those 2 ions are actually going to want to repel. So I want to make sure that all of my negatives are in fact touching my positive. So I'm going to go ahead and I'm going to draw another bromine down here. Remember, a bromine is going to have a square bracket because it's an ion. It's going to have a negative charge. And to be totally correct, I'm going to go ahead and I'm going to show that full valence shell. And my last bromine could be placed up here or it could be placed down here. It actually doesn't matter. There's no totally correct way to do this. I'm going to place it up here. So bromine, square bracket, square bracket, negative charge, and my valence electrons around here. Now there is actually a shortcut that a lot of chemists will take as well too. You might see it in university. I'm going to go ahead and I'm going to show it to you now. So the shortcut that you could take is you can actually use brackets to represent how many ions you have. So I'm going to start with aluminum. And aluminum, remember, I only have 1 of these. So I am actually not going to list anything because I only have 1 of them. But bromine, I'm going to draw myself a bromine here. Square brackets to show it's an ion. Square brackets to show it's an ion. It's got a negative charge. Now bromine, remember, I actually have 3 of these. So I'm going to use brackets around bromine. I'm going to put a bracket here. I'm going to put a bracket here. And I'm going to put a little tiny 3 here. And that's another way that I could actually represent the fact that I have 3 bromines. So you can choose to draw it like this. You can choose to draw it like this. This is a way we actually teach in grade 11 chemistry, but in a lot of university level classes, you might see it like this. This is totally fine. Last thing we want to do is check to make sure that we're right, because why wouldn't you want to make sure that you're right? So you want to check for that charge balance. So charge balance, I'm going to take my positive 3, and I'm going to subtract from it 1, 2, 3 negatives. Well, positive 3 minus 3 negatives is going to be equal to 0. I have charge balance, therefore this is a correct ionic compound. All right, now that I've mastered ionic compounds, we're going to take a look at molecular compounds. Some students find these a little bit more challenging. I always just like to think of them in like a puzzle. So if you like puzzles, you will totally understand this. If not, you're going to get really good at them, I promise. So just a reminder, or molecular compounds, what they are. They're two or more nonmetals. They're held together by a covalent bond. A covalent bond, remember, is the sharing of electrons. So we don't see the transfer of electrons anymore. We're now going to share electrons in order to be full. The difference in electronegativity is going to be equal to or less than 1.7. There's a couple more steps when you want to draw a Lewis diagram of a molecular compound. The first thing you have to do is you have to identify what's called the central atom. So in this case, we're not just going to be dealing with 2 or 3 or 4 different atoms. We're going to be dealing with multiple atoms. So the biggest thing you have to do is you have to identify what's going to go in the middle of your diagram. We call that the central atom. This is typically the one with the less electronegativity. So I'm going to go ahead and teach you this rule of thumb that typically it's whatever has the least electronegativity. However, there's a couple kind of tips and tricks I'm going to show you that's going to make it easier to identify the central atom. You want to arrange the other atoms around that central atom. You then want to sketch the valence electrons for each atom, and you want to ensure that each atom has a full valence shell by forming single, double, or triple bonds. So that's your rough guideline that you're going to go ahead and you're going to follow when we're drawing Lewis diagrams. Again, I think the easiest way I can explain it to you, though, is to show you. So I'm going to show you with nitrogen trifluoride. So the first step is still going to be the same. The first step is going to be, how do I know what I'm working with? I'm going to start with my rough work. I'm going to draw nitrogen. I'm going to draw fluorine so I can actually see what I'm working with here. So nitrogen is in the 15th column on the periodic table. That means that it has 5 valence electrons. I'm hoping that you realize how important it is that you actually kind of have these valencies memorized. So hopefully at the top of your periodic table, you've written how many valence electrons in each column. If not, I would do that now just to make it easier for you. Fluorine on the periodic table is a halogen. It's group 17. Group 17 has 7 valence electrons. So I'm going to go ahead, I'm going to draw 7 valence electrons in here. And now I can at least see what I'm working with in order to combine. So step number 1, I want to identify the central atom. Now this says the central atom is the one with the least electronegativity. So if I actually use an electronegativity chart, which is kind of a pain in the butt, but if I do use an electronegativity chart, I'm going to see the least electronegativity is nitrogen. So that means nitrogen would go in the middle. So that rule usually works. The rule that I like to say always works, though, but you got to think about it a little bit, is which one has the most bonding potential. So what I mean by that is which one wants to form the most bonds. Whatever's going to be forming the most bonds, you want to put in the middle, and you're going to branch off of it. So nitrogen, in order to be full, wants 1, 2, 3 bonds. So nitrogen's going to be forming 3 bonds. Fluorine, to be full, only wants 1 bond, so fluorine's only going to form 1 bond. Nitrogen wants to form 3, fluorine only wants to form 1. Nitrogen has more bonding potential. It's going to be the central atom. So I'm going to put nitrogen in the middle here, and I'm going to go ahead and I'm going to draw nitrogen's valence electrons. So I'm going to put its 5 valence electrons. Now I want to arrange my other atoms around the central atom. So I have 3 fluorines and I have 4 sides to pick from. So hopefully you can see that I'm probably not going to put a fluorine up here, because look at this side is full. This side already has 2 electrons. So these electrons aren't looking to form any bonds. This side, however, this side and this side all want an extra electron. So I'm going to put a fluorine here, and I'm going to put a fluorine here, and I'm going to put a fluorine here. Now my next step is to add my valence electrons to fluorine. I'm going to cheat a little bit. So look at fluorine on this side. This is the side of fluorine that wants to gain an electron. So what I'm going to do is I'm going to take this side and I'm actually going to angle it inwards. So for example, for this fluorine, that 1 free electron that fluorine has, I'm actually going to go ahead and I'm going to place it towards nitrogen because it wants to form a bond with nitrogen. Down here, that 1 free electron fluorine has, I'm going to place it towards this direction, and then I'm going to fill the other sides of fluorine. Is that allowed? Of course it's allowed. And it's going to make your life way easier when we draw this Lewis diagram. Again, fluorine, that one free electron, I'm going to place towards the inside, and I'm going to place the other pairs of electrons around the outside. Now my next step is to ensure that each atom has a full valence shell by forming double, single, or triple bonds. So let's take a look at this fluorine here. This fluorine here has 1, 2, 3, 4, 5, 6, 7 electrons. It wants one more, so it is going to share with its neighbor, nitrogen. By circling these two dots, I'm indicating that that's an example of a shared bond, a covalent bond, and it's going to be a single covalent bond. This fluorine has 1, 2, 3, 4, 5, 6, 7. So it's going to go ahead and it's going to share with this nitrogen here. And this fluorine, same idea, is going to share with this nitrogen here. Now, technically, this is a correct Lewis diagram, but it looks awful. It looks terrible, right? This is really messy. So what we're going to do is anytime that I circle these dots, I'm actually going to replace that with a straight line. So remember from the note before, from the earlier part of the note, a single bond could be represented like this, or a single bond could just be represented as a straight line. So I'm going to go ahead and I'm going to replace these circled electrons with straight lines instead. And we're going to see how much neater this diagram is going to get. So I'm going to erase this. This is such a giant eraser for such tiny dots. I'm nervous here. Ooh. It's kind of okay. So we're going to go ahead and we're going to draw, instead of those circles, I'm just going to draw a straight line. I'm going to draw a straight line. I'm going to draw a straight line. That looks so much better. And this is my Lewis diagram of nitrogen trifluoride. Now, the last thing you want to do is make sure your central atom is happy. You want to make sure your central atom has 8 as well, too. Remember, each of these lines represents 2 electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons total on my central atom. Everything is happy. This is my correct Lewis diagram showing the sharing of electrons. All right, so we're going to go ahead and we're going to start this next one here. So all that I've done is I've placed your rough work first. So in your rough work, you can see I've drawn a carbon, I've drawn a hydrogen, and I've drawn an oxygen for Lewis structures. Carbon, of course, has 4 valence electrons. It's in the 14th group. Hydrogen has 1 valence electron. It's in the 1st group. And oxygen has 6 valence electron. It's in the 16th group. Now, hydrogen is actually very tricky. So I'm going to tell you why hydrogen is tricky for 2 reasons. The first reason is even though it only has 1 valence electron, remember hydrogen is one of the only elements that doesn't follow the octet rule. So hydrogen is not looking to have a full shell of 8. Hydrogen is only filling that first shell on the Bohr-Rutherford diagram, and that first shell is happy with 2. So hydrogen only wants to have 2 electrons, so hydrogen is only looking to form 2. The second reason hydrogen is weird is going to go along with this first rule when we identify our central atom. So we said a general rule of thumb is it's typically the electron or the element that has the least electronegativity. So if you were to use an electronegativity chart here, you would actually find that hydrogen has the smallest electronegativity. However, hydrogen is not the central atom in this case. So a more reliable way to figure out the central atom is to use that bonding potential. So oxygen here has 6 valence electrons. That means oxygen is looking to form 2 bonds in order to be full. Hydrogen is only looking to form 1 bond to be full. It's only looking to gain 1 electron, whereas carbon is looking to gain 4 electrons because it only has 4. So carbon is looking to form 2 bonds. Hydrogen is looking to form 1 bond. Carbon is looking to form 4 bonds. So we would go ahead and we would say our central atom would be carbon. It's looking to form 4 bonds. So I would place carbon in the center, and I would place its valence electrons around it. Now, it actually doesn't matter where you place hydrogen or oxygen because all sides of carbon need an electron. Each side needs an electron, so you can actually go ahead and you can place them wherever you want. So I'm going to place a hydrogen here. Come on. I'm going to place a hydrogen here. I'm going to place a hydrogen up here. And I'm going to go ahead and place an oxygen down here. Now, again, I'm going to cheat when I place my valence electrons, and I'm going to make sure that all free valence electrons are centered towards the middle. So what I mean by that, for hydrogen, it has one electron, and I'm going to go ahead and I'm going to point it towards the middle. This hydrogen is going to have one electron, so I'm going to point it towards the middle. And my oxygen has two free electrons. I'm going to place one of my free electrons towards this side, one of my free electrons towards this side, and I'm going to put my pair of electrons away from that central carbon. Now, next up, I want to make sure that everything is full. Let's start with hydrogen. Remember, hydrogen only wants to have two to be full, so that means it's going to share this electron with this carbon. This hydrogen, again, only wants to have two to be full, so it's going to share this electron with carbon. And then down here, we can see oxygen actually has two free electrons, and carbon has two free electrons. So in order to make this happy, we're going to have a pair of electrons that are going to share here. And we're going to have a pair of electrons that are going to go ahead and are going to share here. Now, again, this doesn't look the best. So what you want to do is you want to go ahead and you want to replace those circles with single lines. I'm actually just going to redraw this. I think that's probably faster. So I'm going to put my carbon here. And instead of drawing this circle with these dots, I'm going to draw a straight line and a hydrogen. Same idea here. Instead of drawing this circle with the dots, I'm going to draw a straight line and a hydrogen. And lastly, instead of drawing these two shared bonds, I'm going to draw a double bond. It's going to look like this. And I do still want to include any electrons that aren't in my circles. So I want to include the two electrons at the top here, and I want to include the two electrons at the bottom here as well too. Now, I realize that there might be a couple of different ways to draw this. Maybe you had your oxygen on this side. Maybe you had your oxygen up here. That's totally fine, as long as you have carbon in the center, as long as you have oxygen and carbon with a double bond, and oxygen has two additional electron pairs, two additional lone pairs, and as long as your hydrogens each have single bonds, then we're happy. We don't worry too much about the geometry yet. That's something we're going to cover more in grade 12 chemistry. So now what I want you to do is I want you to actually take a look at each of these Lewis structures, and I want you to go ahead and I want you to pause the video and I want you to try to draw each of these Lewis structures yourself. Now, first of all, you're going to want to make sure, is it an ionic compound? Is it a covalent compound? You want to make sure you draw the right diagram. And then after that, you're going to go ahead and you're going to draw them each for me. So we hope that you pause the video, right? If you pause the video, these are going to be just me going over them quickly because these are going to be your actual solutions. So I'm going to start with ionic compounds. The only one of all of these that's going to be ionic is going to be barium chloride down here. So to draw barium chloride, all I want to do is I want to draw the ion of barium. The ion of barium is Ba. I use my square brackets to show it's an ion. And it has a charge of 2+. Then I'm going to go ahead and I'm going to draw my chlorine. My chlorine has gained an electron. So if it's gained an electron, it's got a charge of -1. Now I actually do have two chlorines in this case, so I'm going to go ahead and I'm going to use those brackets. Do I have room? Maybe. And I'm going to place a little 2. Can I squeeze in a 2? I'm going to place a little 2 there to show that I have two chlorines. If you drew two chlorines in, that's great. You could have put another chlorine here or another chlorine here. We do have charge balance. I have two positive charges. I have two negative charges. That's going to indicate charge balance. Now up here, I'm going to go ahead and I'm going to draw my Lewis structure now for H2S. In order to figure out which one is your central atom, you want to go with the least bonding potential. So sulfur has 6 valence electrons. It wants to form 2 bonds. Hydrogen only wants to form 1 bond. So I'm going to go ahead and I'm going to put sulfur in the middle. By putting sulfur in the middle, I'm going to go ahead and place its 6 valence electrons around it too. So 1, 2, 3, 4, 5, 6. Hydrogen has 1 valence electron. So I'm going to go ahead and I'm going to place my hydrogen here. And I'm going to place a second hydrogen here. This hydrogen is going to have 1 valence electron. This hydrogen is going to have 1 valence electron. And you can see that I'm actually just Gonna connect the dots this time, hopefully make a straight line. Yeah, it's not too bad. And you're gonna see that my structure is gonna look like this. I have my sulfur, and I have a single bond between my sulfur and this hydrogen, and I have a single bond between my sulfur and this hydrogen here. Now I've got H2O2, hydrogen peroxide. So in this case, I've actually got 4 different atoms. So sometimes students struggle trying to figure out what the central atom is. So let's go with our whole bonding potential. Oxygen has 6 valence electrons, so it wants to form 2 bonds. Hydrogen only wants to form 1 bond. So oxygen wants to form more bonds. Oxygen's going to go in the middle. Tricky part, I have 2 oxygens. So I'm going to put 1 oxygen here, and I'm going to put another oxygen here. They're both going to be the middle. Now I'm going to go ahead and I'm going to put my electrons for oxygen in. Again, I'm going to cheat. So my electrons for oxygen, I'm going to have my lone electrons facing towards the middle. So I put 1 lone electron here, and I'm going to put another lone electron here. And same idea, I'm going to have my lone electrons facing the middle. So I'm going to put 1 lone electron here, and I'm going to put 1 lone electron down here. Now I have to place in 2 hydrogens. Well, I'm hoping that you're going to see that I want to place my hydrogens where there's lone electrons. I see 2 lone electrons down here, so I'm going to place 1 hydrogen down here with my electron. I'm going to place my other hydrogen here with my electron, and again, we're going to try to play connect the dots, and we're going to see that these electrons are going to share here. These electrons are going to share here. These electrons are going to share here. And this is my hydrogen peroxide, a single bond holding together my oxygens, a single bond holding together each oxygen and each hydrogen. Let's take a look at this now. For my central atom, well, hydrogen wants to gain 1 electron. So it's got 1 bond it wants to form. Carbon has 4 valence electrons, so it wants to have 4 bonds it wants to form. Nitrogen has 5 valence electrons, so it wants to have 3 bonds that it wants to form. So in this case, I would put carbon in the middle because it has the most bonding potential. It has 4 bonds that it wants to form. Nitrogen, I'm going to put over here, and again, I'm going to cheat. I'm going to go ahead and I'm going to place nitrogen's 3 valence electrons towards the middle, and the side that's full, I'm going to place off to the side because it's not going to be involved in bonding. Lastly, my hydrogen, I'm going to place over here, and I'm going to go ahead and I'm going to place my 1 lone electron here. Now, you could have put your hydrogen up here, you could have put your hydrogen down here. It really doesn't matter where you put it. Now, our next goal is to go ahead and make sure that everything's happy. Hydrogen is probably the easiest one to start with. It only wants 1. So I'm going to go ahead and I'm going to draw my 1 there. Now, nitrogen's a little bit trickier because nitrogen wants to have 3. Well, if I take a look, carbon also wants to have 3. So again, we're going to play connect the dots. So we're going to have this bond, we're going to have this bond, and we're going to have this bond. So what we can actually see is I'm forming a triple bond. I'm going to write this out a little bit better below. So carbon and nitrogen is going to form a triple bond. It's going to share 3 electron pairs. Nitrogen is still going to have 1 pair of lone electrons on the side here, and hydrogen has formed a single bond with carbon. Down here, again, I have to figure out which is going to be my central atom. Well, carbon is looking to form 4 bonds, whereas hydrogen is only looking to form 1 bond. So carbon is going to go ahead and it's going to go in the middle. I have 2 carbons. That's okay. That means they both go in the middle. Each carbon, again, has 4 valence electrons. Here I have 4 valence electrons. And hydrogen, I can really place wherever I want. I'm going to go ahead and I'm going to place my hydrogens here. So I'm going to put hydrogen here. And I'm going to put a hydrogen here. Ooh, that didn't finish my arm. There we go. And I'm going to put a hydrogen here. For hydrogen, again, I'm going to cheat. So I'm going to take that lone pair, that lone electron, and put it towards the middle. And I'm going to take that lone electron and put it towards the middle. So let's start with hydrogen. That's the easiest one. So hydrogen is going to want to form with carbon. Hydrogen's going to want to form with carbon. Now, by doing that, we can see left, we have 3 electrons that aren't happy on carbon, and we have 3 electrons here that aren't happy on carbon. So what they are going to do is they are going to form bonds with each other. So we're going to have a bond here, we're going to have a bond here, and we're going to have a bond here. Again, that doesn't look very nice, so I'm going to go ahead and I'm going to redraw that. I'm going to have my carbon down here. I'm going to have my carbon here. There's a triple bond, so I'm going to go ahead and draw a triple bond between here. And then I've got my hydrogen here and my hydrogen here. Now you can see I haven't really left myself up. You know what? I have enough space. We're going to go for it. I was going to say I'm going to erase this. We're not. We're going to make this work. So for our last one here, again, you want to figure out bonding potential. So here, my carbon is looking to have 4 bonds form, right? This carbon has 4 bonds. It's looking to form 4 bonds. This hydrogen is only looking to form 1 bond. And this chlorine has 7 valence electrons, so it's only looking to form 1 bond as well too. So carbon is looking to form the most bonds. I'm going to go ahead. I'm going to put carbon in the middle. 1, 2, 3, 4, and then I'm going to arrange everything else around it. It doesn't actually matter the order that you do it in, so I'm going to put my 1 hydrogen at the top here, and I'm going to put a chlorine here, and I'm going to put a chlorine here, and I'm going to put a chlorine here. Again, I'm going to cheat and put my free electrons towards the middle. So I'm going to put my 1 free electron for hydrogen towards the middle. I'm going to put my 1 free electron for chlorine towards the middle. That means the other sides are still going to be full. I'm going to put my 1 free electron for chlorine towards the middle. That means my other sides are still going to be full. And I'm going to put my 1 free electron for chlorine towards the middle. That means my other sides are going to be full. Now I just play connect the dots. So I'm going to go ahead and connect these dots. I'm going to connect these dots here. I'm going to connect these dots here. I'm going to connect these dots here. And you can see that we're getting full. So you can see that this chlorine has a single bond. This chlorine has a single bond. This chlorine has a single bond. This hydrogen has a single bond. To check and make sure we're right, let's make sure everything is full. So this chlorine has 1, 2, 3, 4, 5, 6, and this line counts for 2, 7, 8. This chlorine has 8, this chlorine has 8, and if I count for carbon, carbon has 1, 2, 3, 4, 5, 6, 7, 8. You're going to notice, again, the more that you do this, the more patterns that you're going to see. So you're going to notice that here, carbon was actually always the central atom. That's actually a whole branch of chemistry called organic chemistry, and we're going to study that in grade 12. So again, the more you do these diagrams, the better you are going to get at it, which is why you have a nice big assignment for me now. So on that assignment, you're going to go ahead and you're going to practice drawing Lewis diagrams. My best advice for you, identify the type of compound first and draw all the compounds together. So for example, notice I identified ionic compounds first, and then I drew all the ionic compounds. I saved the covalent compounds for last. So good luck. Email me with any questions, and we'll move on to our next lesson. Now we're ready to actually look at naming compounds, now that we understand how to draw them. So our next lesson, our next branch of this unit, we're going to look at naming compounds.